Welcome to an introduction to chemistry, excuse me, where we're going to be talking about what chemistry actually is, why we study it, a little bit about the scientific method, a little bit about qualitative versus quantitative observations, and finally, we're going to take a look at hypothesis versus theories versus laws. So what is chemistry? Well, chemistry is really just simply a study of matter and its transformations. Well, what does that mean? If we take a look at liquid water, this L here means liquid, and we're changing it into solid water or ice. Water is matter. It takes up space. It is something that we can hold on to. So matter could be anything from oxygen to copper, nitrogen, ammonia, or water. So if we're changing water from liquid form to a solid form, that's a transformation. And so what actually happens during that transformation within water? The other thing that we study is the connection between molecular and macroscopic world. So in other words, we've all seen water freeze and become ice. And what we look at is, well, we can't really see when that water becomes ice what is actually happening to the chemical water. So in chemistry, we study that connection between what's happening molecularly and what happens macroscopically, what happens in terms of that water becoming ice. There's several reasons to study chemistry besides just learning about life's little mysteries. We like to learn the fundamental models of chemistry. Chemistry happens all around us constantly without us really thinking about it. And so to better understand the world that we live in, it is important that we study the fundamental models of chemistry. Second, we gain a technical perspective on current events. Chemistry, in my opinion, is the backbone to all of the other sciences. Without chemistry, biology doesn't make sense. Without chemistry, geology and earth science don't make sense. Physics is the study of things largely chemical. So chemistry is kind of that backbone, and so anytime anything happens scientifically in our world, it's a good bet that chemistry has something to do with it. So if we better understand that, we can better understand the world that we live in. Finally, there will be times this year where you feel like you're almost in a math class. It's not true. You're still in chemistry, but we are developing good problem-solving skills. And one of the ways that we problem solve in chemistry and in all sciences is through the scientific method. And the scientific method is nothing more than a systematic procedure for solving problems. And so many of you have seen something similar to this probably, where we ask a question, do background research, construct a hypothesis, test that hypothesis with an experiment. And then there's some checks and balances here, but eventually we want to collect and analyze data so that we can draw conclusions based on our experiment and our hypothesis. And then if our results align with our hypothesis, then we communicate those results with other scientists. If they don't, then we either need to go back and reconstruct a brand new hypothesis, or we need to correct our hypothesis a little bit. And so speaking of that, let's talk a little bit about observations. Another way that we can talk about observations is many times is collecting data. All right, so observations, collecting observations or collecting data. This is the foundation for the scientific method. Without collecting good data, then we cannot say that our conclusions have any solid basis. So we'll spend a lot of time looking at our observations and our data and trying to collect good, solid data. Data is most useful when it's collected under controlled environments. And what I mean by controlled environments is purely that we're doing experiments, that we are controlling most of what is happening in the experiment. We are only changing one item at a time. That's very important. Sometimes in the real world, it's hard to mimic what is happening in the real world in an experiment, but as often as we can, we'd like to collect our data in controlled experiments. There's two types of observations. The first type is qualitative. Qualitative with the root word quality in it. So quality. And then the other type is quantitative, and the root word there is quantity. Oops, I forgot the N here. Quantity. T-I-T-Y. Quantity. Qualitative is talking about a description, the quality of something, the description, and we're usually using our senses when we talk about a qualitative observation. We are not going to measure anything with a qualitative description. We are talking about things such as color or texture or smell. Something that has to do with our senses. And we cannot measure texture. We cannot measure smell with any good measuring tool. But qualitative observations are important. Quantitative measurements, quantitative observations will have a number and a unit, and units are going to be very important for us in chemistry. Anytime you do any type of problem, make sure that you include the units. Quantitative observations are measured. And here we're talking about things like length or mass or density. ITY. This year we'll talk a lot about volume. Many times we'll measure temperature, so on and so forth. There are many quantitative measurements that we can make in chemistry, but the important thing is quantitative means we're going to have a number and we're going to have a unit. Qualitative, we are not going to have a number and unit. It is not measured. All right, let's talk a little bit more about hypotheses, theories, and then natural laws. A hypothesis is a tentative explanation. We make this explanation prior to doing an experiment, and it is actually designed to guide the experiment. These explanations must be testable. Many times they will be an if something happens, then this will happen. We call it the if-then statement. And so we must be able to test that if-then statement to make sure that it's true. If it does conflict, and we talked a little bit about this before, if it does conflict with your results in an experiment, then you must go back and either reject it or you must correct it and retest it. If you reject it, then you start over from scratch and you build a new hypothesis. Theories, on the other hand, are well-tested explanations for experimental data from a set of hypotheses. All right, so a couple of things here. One, they're well-tested. We're making an explanation after the experiment. We have many pieces of data that we are explaining from a set of hypotheses. So it's not just one experiment that gives us a theory. It is many experiments, many hypotheses, well tested. All of these hypotheses are giving us information and data that support a similar concept. And so these may be discarded, they may be refined, they are not laws, but they are pretty solid until we get a new set of data that makes us refine them. A good theory has several things. A good theory is going to explain all the available data that has to do with that explanation. We are not going to subtract any of the data. It's going to be able to predict results for future experiments. Based on your explanation, people should be able to predict results of experiments that they are making. It's going to show a connection between the hypotheses that the theory is based upon. And then finally, it may suggest new lines of work or new ways of thinking about a certain situation. All right, so hypotheses were about tentative explanations guiding our experimentation. Theories is about a well-tested explanation from a whole set of hypotheses, and natural laws are going to summarize patterns in a large amount of data. Many experiments, many hypotheses, several theories all being summarized together to summarize the patterns within that data. They often only apply under special conditions. The conditions have to be perfect for these natural laws to stay true to what they're saying. And then often they're a description of nature. They're not necessarily facts. They're a description of what happens in nature all the time. All right, so that's the end of our first note session. We will see everybody in class.